In the last lecture, we started discussion on some of the major components, major modules, which are required to form the data path while designing a processor. So we'll continue on that and try to put those together to form a simple design of a processor. As we had identified, excuse me, the major blocks in the data path are ALU, shifter, multiplier, register file, and there's memory which needs to be connected to the rest of it through some data path which manipulate transformation from bytes to words and words to bytes and so on. So we had discussed all these modules except for multiplier. Let me spend a few minutes on that, and then we will see how we can put not necessarily all of them. In the simple case, we'll focus on very simple set of instruction without involving shift, multiplication, or byte manipulation. So let's look at the instructions which are there in ARM instruction set for multiplication. I had talked about MUL and MLA, which stand for multiply and multiply accumulate. These produce 32-bit results, and there are 4 more instructions which produce 64-bit result. So if you are multiplying two 32-bit numbers, the result can actually go up to 64 bits. But if numbers are small, it can be contained within 32 bits. But if number is large, there will be overflow. So there is a provision for instruction which retain entire 64-bit result. Okay. There are in 2 variants. One is signed and unsigned. So SMULL, the last L indicates that it is long multiplication. So signed multiply long means that you're doing signed multiplication, and long indicates that the result is 64 bits. So correspondingly, there is SMLAL, signed multiply accumulate long. And then there are 2 unsigned variants. So you would be wondering why this distinction of signed and unsigned is not there in MUL and MLA. So let's try to understand that reason. So suppose, just to understand the idea, let's look at 4x4 unsigned multiplication. Suppose first operand is A, 4 bits are A0, A1, A2, A3. The next operand is B with bits B0, B1, B2, B3. Okay. So let's A is the multiplicand and B is the multiplier if you want that distinction. What multiplication involves is that you multiply A with B0, multiply A with B1 and so on with each bit of B and add them with appropriate shift or multiplication by power of 2. Okay, so here first row you're multiplying by 2 raised to power 0, then 2 raised to power 1, 2 raised to power 2, 2 raised to power 3. If you add all these, you'll get a product which can be at most 8 bits. Now, if you do signed multiplication, and you know that the signed numbers can be represented by, for example, B, the number B, which is being used as a multiplier here, can be expressed as minus B3 into 2 raised to power 3 plus B2, 2 raised to power 2 plus B1 into 2 raised to power 1 plus B0 into 2 raised to power 0. Okay, so if you do that, you will get the numerical value of B. It could be positive or negative depending upon what the bits are. So now A is also a signed number here. Therefore, as you're doing a wide addition, we extend the sign bit. Okay, before you could add, instead of putting zeros as we did in case of unsigned multiplication, we extend the sign bit. Okay, so the difference is coming here because the last one is different and the sign bits are extended. Now let's understand what happens when a number is multiplied by -1. So if B3 is 0, then this row is 0. But what happens when B3 is 1? Then essentially this multiplicand is multiplied by -1, or we are taking negative of it. How do we take negative? We take its 2's complement, right? Suppose x is a number, n-bit number, and let's look at the rightmost one in this. So suppose xk minus 1 is the rightmost one. K could be anywhere from 1 to n. Then we can write the number as this. Towards right of xk there is 1, and then remaining are zeros. Okay, so in an extreme case there may not be any zeros here, but there could be a few zeros also, right? So the point is that there is some bit xk, following that there is 1, and then possibly some zeros. Now let's find 2's complement of this. So first we find 1's complement. So I'm writing x bar is that each bit is complemented. 1 becomes 0, 0 becomes 1, and these x bits are also complemented. Now what will happen when you add 1 to this? Okay, so imagine that you add in the rightmost position, a 1 is added here, and that will become 0, carries will make everything 0, and you'll have a 1 there. So it's like you have 999 and you add 1 to that, you get 1000. So in similar sense, minus x, which is negative of x, is that these bits are complemented, but towards right of xk we got what we had originally. Okay, so what you can say is that the rightmost k bits remain unchanged and left n minus k bits get complemented. This is one way of looking at finding 2's complement of a number. Okay, you locate the rightmost one, and then right k bits remain unchanged and remaining get complemented. So now let's apply this insight into this picture of signed and unsigned multiplication we were trying to compare. So I'm taking a case that let's say k is 2. Okay, so 2 bits are same and 2 bits are complemented. Okay, so there'll be at least 1 bit which remains unchanged. Okay, there may be more bits, but at least 1 bit will remain unchanged because k has to be greater than or equal to 1 and less than or equal to n. So now you can see that there is a common part here. Okay, when you sum these rightmost 4 bits are going to be same whether you interpret the two numbers as unsigned and multiply, or you interpret them as signed and multiply. Okay, so that's the idea. When you do MUL and or MLA, internally is 64 bits of result are produced, but only rightmost 32 bits are retained. And as long as your result is fitting in that, result is small enough, you'll get the correct result. So if you interpret operands as unsigned, those 32 bits will give you correct unsigned product. And if you interpret if you interpret these operands as signed number, then the rightmost 32 bits will give you correctly signed product. Okay. So is that point clear? That is, I think that's something important to understand.
So can you repeat the last part once?
Yeah, what I'm saying is that if the result Okay, so let's put it this way. So basically, in the processor, two 32-bit numbers get multiplied as signed numbers. Okay, and a 64-bit signed product is generated. But when you use MUL instruction or MLA instruction, then only rightmost 32 bits are retained. And it turns out that whether you interpret the operands as signed or unsigned, the uh, right half is same. It doesn't change. Okay, so if you interpret operands as unsigned, you can interpret the result as unsigned. If you interpret operands as signed, you can correctly interpret the result as signed. Okay, so there is a single instruction which does the job. So for example, let's say uh, suppose one of the operands is 1, other is -1. Okay, so 1 will be 31 zeros followed by 1, and -1 will be all 32 bits are 1. So now these are 2-bit patterns. Okay, 31 zeros followed by 1 is one operand. 32 ones is second operand. If you interpret these numbers as signed numbers, then you have 1 and -1, and the product should be -1. But you interpret these as unsigned number, you have 1 and 2 raised to power 32 -1. So the result should be 2 raised to power 32 -1. So the result would be actually all 32 ones, and depending upon what interpretation you use for the operand, you can use the same for the result. Okay, so now suppose let's try to do, suppose you were to build a multiplier. Actually, you are doing design and you want to express that in VHDL. Is there anyone who has no basic familiarity with VHDL? So I'm sure in logic design course that has been done. You may not have done enough practice, but I'm sure what I'm showing here could be understood. So now we suppose we are trying to design a module which takes two operands. I'm calling them as AS and BS, and I'm declaring them as signed numbers of 32 bits. Okay, so I'm not declaring these as integer. I want a definite size. So therefore I'm going to talk of signed and unsigned data types. Okay, so signed is like a bit vector. Essentially, you can freely interchange uh, between 32 STD logic vector or bit vector with the signed and unsigned. Okay, so essentially what I'm saying is that here is a 32-bit number which I'm going to interpret as signed number, and the result is 64 bits. Okay, again signed. So you can simply write PS. You can assign AS star BS to PS. Okay, that means output is a product of the inputs. So suppose these were input ports and that was output port. Now, if you synthesize this, let us say you do that for FPGA, where the building blocks are 18 by 18 multipliers. Okay, so actually, to be more precise, in one specific FPGA, which we often use in the lab, these building blocks are called DSP48E1, and FPGAs have these pre-designed uh, multiply accumulate units. So strictly speaking, it is 25 by 18, but just for symmetry, I'm writing these as 18 by 18 multiplier. So to do a 32 by 32 multiplication, it needs 4 of these. Okay, so using its capability of 16 by 16, 4 multipliers get used for that. Similarly, if you were doing unsigned multiplication, you have inputs interpreted as unsigned, output interpreted as unsigned, and uh, you can still do this multiplication. So here we have a full-fledged 64-bit product here. So now this multiplication has to be different from that multiplication. Okay, because when you're looking at the entire product, 2n-bit product, then signed and unsigned give different result. But if you look at the right half, the result is same. So what is the meaning of this multiplication depends upon the operands. So here the synthesizer creates a signed multiplier, and in the second case it will create an unsigned multiplier. So if you want to implement both the instructions, signed and unsigned, just a minute.
Sir?
You would need to combine the result. Yeah.
So why would we require 4 FPGA? It's an 18 cross 18.
No, not 4 FPGAs. Each FPGA has a number of this kind of modules. Okay. Each of those modules. So in FPGA there is there are lookup table, there are multipliers, there are memory module, and so on. And the process of synthesis takes your VHDL description or description in other language like Verilog and produces a design which is built out of these modules which are there in the FPGA. Okay, so what I'm saying is that for doing this part, it will require 4 of those DSP48 modules because each module has 18 by 18 multiplication capability.
Yes, sir.
Okay, so now you want to let us say you want to implement smul and umul, these two instructions, right? What you would do is let's have inputs and outputs not interpreted as signed or unsigned. We simply say that OP1, OP2, the two operands, are STD logic vectors of 32 bits, and the result is STD logic vector of 64 bits. So these STD logic vectors we are going to interpret differently to create two different multipliers. So PS, which is a signed number 64 bits, and PU, which is unsigned number 64 bits. We say that PS is signed interpretation of OP1 multiplied by signed interpretation of OP2, and PU is unsigned interpretation of OP1 multiplied by unsigned interpretation of OP2. So this I read this as signed interpretation of OP1. So basically, I'm doing a type conversion here. Okay, type conversion from STD logic vector or bit vector to a signed number. So it's just an interpretation. There is no physical logic or gates required to do that conversion. All right, it's only a matter of interpretation. So this would result in synthesis of a signed multiplier. This will result in synthesis of unsigned multiplier. And the result, the final result we want to produce, we select either PS or PU, but we are converting these to STD logic vector. Okay, so again that's an interpretation back to a logic vector. So when instruction is smul, we pick up the signed product, otherwise pick up the unsigned product. So it could be implemented using 4 plus 4, 8 DSP units. But what we observed was that it tries to optimize, because out of 4 units of the signed multiplication and 4 units of unsigned multiplication, one is doing exactly same job, same input output, and can be optimized out. But it tried to use 7 DSPs, so reduce 1, but the interconnection became fairly complex and there was failure in routing stage. So anyway, I think that's a more practical limitation. If you don't optimize, this could be implemented using 8 DSP units. Okay, but there is another way which I'll discuss now. So question here is that how do we use a signed multiplier to do unsigned multiplication? And answer to that is 0 extend the operands. So add one more bit to the operands, which is 0. Even if uh, even if the leftmost bit was 1, now it will start looking as a positive number. Okay, so in if two numbers are unsigned, the leftmost bit could be 1 or 0. Still, we interpret them as unsigned or positive numbers. So we add one more bit, which is 0, and then feed these to a signed multiplier. Signed multiplier looks at them as positive numbers and gives correct results. So with that idea, uh, we still have OP1, OP2 as STD logic vectors of size 32. Result is STD logic vector of size 64. And now we produce a 66-bit product, 66-bit signed product, and pick up 64 bits out of that. So PS is an intermediate signal which is signed 64-bit number. X1, X2 are two intermediate bits of type STD logic. So these two statements are crucial. We are looking at, yeah, is there a question?
Yes, sir. Why does P signal PS has 66 bits?
Yeah, because we are extending, what we are doing is, our idea is that we take 32-bit operands, make them 33 by adding a 0 to the left. When we multiply these, we get 66-bit result. Okay, and we pick up 64 bits out of that, throw away the left 2 bits. So OP131, this is the leftmost bit of OP1. If instruction is S-mul, then we do sign extension. Okay, if instruction is U-mul, or that it is not S-mul, then we extend by 0. Okay, so either we extend by the leftmost bit when it has to be done as a sign multiplication, and otherwise for unsigned we extend by 0. So X1 concatenated with OP1 is a 33-bit number. We interpret that as a signed number. But in this case, if it is UMUL, it's going to be positive. And similarly, X2 concatenated with OP2, we interpret a signed number, perform multiplication. So a 32 by 33 by 33 signed multiplier is created because of this multiplication. And we take rightmost 64 bits. Okay, that produces result. So this gets implemented just with 4 DSP, because in this you can see that we are using only one multiplier. Okay, so this was about building a module which can do multiplications of various kinds, right?
Right.
Yeah.
So how can a unsigned number have left? I mean, the most significant bit is 1. This should be positive always.
You see, if you are interpreting, let's just take example of 4 bits. A 4-bit unsigned number has a range from 0 to 15. Okay, if you have a 4-bit number and you want to interpret this as unsigned number, the range of values is 0 to 15. If you have 4-bit which need to be interpreted as signed number, the range is -8 to 7.
Yes, sir. Got it.
Okay, so in unsigned interpretation, the leftmost bit is not interpreted as a signed bit. It is interpreted as the most significant bit with the weightage of 2 raised to power n minus 1. Any more question?
Sir,
Yeah.
so could you please explain again how we are extending the bit to at 0?
Okay, so what we are trying to do is, if you want to do unsigned multiplication, we are extending by 0. Okay, this is what it's a conditional assignment statement which will assign OP131 to X1 if your instruction is small. Otherwise, it will assign 0 to X1. So it's like saying that if instruction is small, then X1 is assigned OP131, else X1 is assigned 0. So we are either doing sign extension or 0 extension, depending upon whether you want to carry out SMUL instruction or UMUL instruction. Well, same thing will hold for SMLA and UMLA. Okay, let me ask you a question. Is the logic circuit for doing signed addition and unsigned addition same or different? So suppose you need to design a 4-bit adder for signed 2's complement number, and second exercise, design 4-bit adder for unsigned numbers. So would you get different answers or same answer?
Sir, same, I guess.
Yeah, guess or you're sure?
Sir, I think same.
Same,
Because,
sir, same.
Yeah, exactly same. So that's the nice property of 2's complement representation. If you had if you have sign magnitude representation of 1's complement representation, then the circuitry for addition would be different. But when you are doing when you are representing sign number in 2's complement notation, the adder is same. Okay. But for multiplication, as we have seen, it is different. So part of the circuitry is same, because right half of the result is same, left half would be different, depending upon the interpretation you want. All right.
Sir,
Yeah.
in this code, X1 and OP1 means that we are concatenating the
Yeah,
signals.
we are concatenating. So 1 bit concatenated with 32 bits, it's forming a 33-bit vector.
Okay, sir.
Okay, so now let's get back to the exercise of processor design, where we're trying to go from instruction set architecture to microarchitecture, right? And instruction set architecture is the lowest level visible to a programmer. Microarchitecture is high level view of the hardware. So we can now look at each instruction as something which changes the state of your processor in some way. Okay, the state of the processor and memory together, state of the entire machine. The processor state is contained in okay, here what I'm showing in this box is the state of the whole machine. I'm trying to show program memory as separate, because assuming that doesn't change. All right. The state therefore is defined by contents of register file, data memory, flags, and program counter. So for this discussion, let's also assume that PC is a different register. It's nothing to do with R15. Okay, we can see if PC happens to be one of the registers, then what changes are required. But suppose we look at it as a separate register. So we have a register file, flags. Yeah, question?
Yes, sir. Like, what does program memory store? Data memory stores the data, right? What does program memory store?
Stores program instructions.
Oh, okay, fine.
So we have artificially split the memory into two parts: data memory, which will be used for load store instructions. Okay, program memory is the one where instructions are stored. So you take address which is there in PC, pick up the instruction at that address, and then modify the state as guided by the instruction. Okay, so each instruction will try to modify the state in some way. So I'm trying to interpret the whole thing uh, as a some kind of state machine. So you have state, you go from, with every instruction, you go from one state to other state. Okay, so the entire behavior of program could be seen as the sequence of state changes that are carried out. Okay, so how instructions are executed? You need to look at the current state. Based on the current state, decide what should be the next state. Okay, and update the state. So what will decide what the next state should be? The instruction, look at the instruction and the current state. Based on that, you decide the next state. So now refining this sequence further, we use the program counter to supply instruction address. Okay, get instruction from memory, read the registers. So think of instruction like add instruction, read the registers, use the instruction to decide exactly what to do, update the PC, update the registers, flags, memory, whatever needs to be updated, you update that, right? And since the program counter gets updated, you repeat the cycle, same thing will happen again. Okay, so now there are different ways you can actually implement this idea. You need to think of what hardware resources you want to use and how you want to manage the timings. So what building blocks are to be used to execute the instruction? This is not something which is unique. Given an instruction set, you could have variation in building blocks. So with one set of building blocks, you design one way. If the building blocks change, you may be able to design differently. Okay, so the set of building blocks is not a unique set. You can have different possibilities here. As far as timings, the question of overall approach to be followed for timings of instruction, and these two are interlinked. For example, depending upon the set of hardware resources, you may be able to do some things at the same time, or you may have to be you may be constrained to do them in a sequence, right? So there is a linkage between these. So if you decide how you want to organize your timings, you would need hardware resources according to that. Or if you have frozen your hardware resources, your timings will have to follow that. So the answer would depend upon the design goals, whether you want a fast design, whether you want a design that consumes low power, or you want a design that is inexpensive. So now let's look at the timing part. There's a question of timings within individual instructions, and there is a question of timing across the instruction. So timing within means that instruction apparently involves many actions. You want to do all these together, or you want to space them out in the form of a sequence. So these actions are timed by clock cycles, and your choice of timing would decide how many clock cycles an instruction takes. So in short, this is called CPI, cycles per instruction, and that's something which is important to understand when you are trying to estimate the performance of a processor. So each instruction is done in a single cycle is one possibility, or instruction takes multiple cycles. So there are various possibilities that exist here. If you choose to, if you're not restricting yourself to a single cycle per instruction, then the question would be that do all instructions take same number of cycles? Okay, so some instruction could take more cycle, some take less number of cycle, or you might say that okay, every instruction has to take same number of cycles. So these are again design choices. What about timing considerations across instructions? So you may say that when one instruction finishes, only then another instruction starts. Or you may say that execution of instructions can overlap. That means before one, suppose you have a sequence of instruction, I1, I2, I3, I4, you can do them in strict sequence. One finishes, then you do the next, that finishes, you do the next, and so on. Or you could allow them to overlap. Now this, there may be some limitations to such overlap, but such overlaps are possible, as we are going to see later. Another
Sir,
question.
do overlaps mean like working in multiple threads?
Overlap means that, let us say each instruction takes 4 cycles. Okay, so first instruction will go through cycle 1, 2, 3, 4, and for the second instruction, don't wait till the 5th cycle. When the first instruction is in 3rd cycle, you can start the next instruction. That also takes its own 4 cycles. So 2 cycles of first may overlap with last 2 cycles of first instruction, overlap with first 2 cycles of second instruction, and so on. So there could be
So,
small
sir, like
overlap.
nested blocks.
Pardon?
Okay. So
Yeah.
nested blocks, are they overlaps? Do we consider them overlaps?
Nested block, what do you mean?
I mean, one instruction calls the other, then the other finishes, then the first instruction finishes, kind of.
Oh, I see. Yeah, technically that is possible. There are some concerns with that. So we'll discuss that later. But such things are possible. That instruction which starts later finishes first. That is also possible.
Okay, sir. Thank you, sir.
So another question is that overlap is one thing, but do you start only one instruction at a time, or you can even start multiple instructions, right? So such designs are also possible. But as you can guess that moment you think of such aggressive schemes, the design becomes more and more complex. Yet another issue is that instructions, do they start in strict program order, or can the order itself be changed? Okay, so you have I1, I2, I3, I4. You do these in same order, maybe with some overlap, but possibility is that you could even change the order as long as the meaning of program doesn't change. Okay, if they are relatively independent, you could even change the order. So lots of possibilities exist, and these are actually used with a view to get high and high performance. Okay, but we'll start with something which is very simple, where only when one instruction finishes, the next one starts. Only one instruction starts at a time. The strict order is followed. Okay, so for first design, this is not necessarily best in terms of speed, cost, or power consumption. We'll take a small subset for purpose of illustration, and then we'll discuss how we can add more. So take a few representative instructions, basically add, subtract, compare, move, load, store, branch and equal, branch and not equal. Okay, it's a fairly representative set, and we will look at only simple forms of these. So for the first design, let's also assume that each instruction is done in a single cycle. Very simplest possible thing. and there's no instruction overlap, no concurrency. Execution is in strict program order. Apart from the CPU data path building blocks, let's also visualize how memory is going to be used. So with memory, we have two inputs, address and data. Okay, address and one output, which I'm calling as data out. The input I'm calling as data in. So it's a block which has 32-bit address coming in, 32-bit data in coming in, 32-bit data out going out, and control signals for memory read and memory write. This tells whether you want to perform read or write. As I said a few slides back, let's separate out program and data memory for the moment. It will allow accessing instruction and data within the same cycle. So this for a single cycle design, actually that is essential. If you want to do every instruction single cycle, imagine what will happen for load store instruction if the two memories were not different, they were same. You would require multiple ports. Actually, technically you can do that if you want to read instruction and data simultaneously from memory. You need multiple ports. In this one, we have one write port and one read port only. So you would read two read ports, and practically memories don't have that. Small register files have multiple ports, but not these major memories. So as far as program memory is concerned, it is similar to data memory, but there's no data in. We only read out of this. So assume that somehow instructions have been put there permanently and can't be changed. So there is a fixed information. This is what we call as read-only memory. So you give an address, out comes an instruction, and we would think of this as this to behave like a combinational circuit. There is an input, there is an immediate response. All right, there is no state. The contents don't change, so we think of this as a combinational circuit. You give an input, and immediately there is an output. No clock goes to it, no control signal goes to it. So let's build data path now with these memories and other components. What we'll do is we'll look at instructions of each category, see the requirement, and sort of put all these requirements together. So for DP instruction, you fetch the instruction, access register file, pass operands to ALU, pass results coming from ALU to register file, and increment PC. These are the things to be done. We'll do all that in a single cycle. So we need to connect output of PC to the address input of instruction memory or program memory. Okay, and instruction is available. Then the instruction has different fields. Okay, some fields specify register number. So we look at the operand register fields. Bit number 16 to 19 in the instruction, and bit number 0 to 3 in the instruction. Okay, so the two operand registers are specified by these fields, and these are used as read addresses for the register file. So we assume that register file has two read ports and one write port. So these 4-bit, two groups of 4 bits coming from instruction are used as address for the register file, read addresses for the register file. Even reading from register file, we'll treat this as a combinational operation, without involving any clock. So the information is just flowing through this as it does in combinational circuit. From instruction address, we get instruction. From the register addresses, we get the contents of these two registers, and these operands get passed to the ALU. Okay, ALU is also combinational circuit. ALU output is connected to the right port of the register file. So WD is the right port, and address where this data is to be written will come from the instruction bit number 12 to 15. Okay, so you can actually cross check with the instruction format we had discussed in the earlier lecture, that you have this field we called as RD, this was called as RN, and this was called as RS. RS or RM? Okay, one of the two. So anyway, these two were operand fields. This was the result field. What else we need to do? We need to get ready for the next instruction. So we need to increment PC. So there is an adder. One input of the adder is PC, other input is constant 4, and output of this goes back to PC. So at the end of the clock cycle, we cause the state change. Okay, so when the clock edge comes at the end of cycle, PC gets PC plus 4, register file gets the result produced by ALU, and ALU had acted on the operands supplied by the register file as dictated by the instruction. Okay, so in the beginning of cycle, we had a new value of PC that there was a flow of information all through this, through the ALU back to register file, and from PC new address computed back to PC, and if you give clock to PC and register file at the end of the cycle, the state change will happen. So that's how this instruction like add, subtract, and so on will get executed in this. What
Sir?
I've not, yeah, just one. What I have not shown are the control signals. Okay, control signals will enable ALU to perform the right kind of operation. Again, those control signals will be derived from the instruction, some of the instruction fields. Yeah.
So writing and reading in the register, it takes place instantaneously. No clock cycle is involved.
Yeah, reading from register file and memories will consider instantaneous. So
Okay.
instantaneous in ideal sense, but there'll be some delay, but no clock required. There is no state change happening, so no clock is required. You give an address, uh, the data which is there comes out, possibly after some propagation delay.
So
And right.
how are the register values incremented like with constants? Like let's say we add R1, R1 4.
Okay.
So how is that 4 passed?
This diagram is looking at uh, adding to when both operands are registers. Okay, second operand could be a constant, so that is not shown here. We need something else for that. So right now, think of this as a circuit which can implement DP instructions where uh, second operand is a register and no shift involved.
Okay, fine. Thank you, sir.
Sir, a doubt regarding the implementation of the project. Wouldn't it be like better if we had some tools like Quartus or Vivado or something from which we can synthesize the thing? Because just implementing it in VHDL can cause a program that actually runs and simulates, but isn't actually synthesizable into circuits or something like that.
Yeah. See what the next set of lab exercises will be involving processor design, and for that you could what I would advise everyone to do is load Vivado synthesizer. Okay.
So Vivado is actually pretty huge. It's some 200 gigabytes. Quartus, on the other hand, is 64 types, which is manageable.
Okay, you send me details of that, and I'll have it checked. Yeah, the plan is to use VHDL as the design language and go through simulation and synthesis both. Okay, so now let's look at another instruction. Suppose we want to implement store. So we'll add some more logic, some more circuitry to allow the same design to do str instruction also. Again, in simple form, uh, where uh, we will not have any auto increment, auto decrement, pre-indexing, post-indexing. Simply, you specify a register and a constant. The address is obtained by adding the two. So you would fetch an instruction, access the register file, compute address using ALU, write data into memory, and increment PC. So we already have this circuit. Now what we want to do is we want to bring in this data memory. The address input of data memory will come from ALU, because in ALU we'll perform addition of register and a constant. So that constant addition would mean that you need to bring that constant from instruction and make it available as second operand in the ALU. So I'm modifying the circuit here, put a multiplexer. DP instruction requires this output of register file to come to ALU, but this LDR instruction requires these 12 bits from the instruction. Extend these to form 32 bits by, this is unsigned extension, so you pad these 12 bits with 20 zeros and bring it as second operand through this multiplexer. Okay. So that takes care of address. Now what about data? We need to store contents of one of the register. So we need to use another field. Okay, in this case, bit number 12 to 15 of the instruction specify the address of the register whose contents are to be written in the data memory. So second read address for DP comes from bit 0 to 3 of instruction, and bit 12 to 15 in case of store instruction. So the output coming from register file is the right data for memory. So that is a store instruction. Now load instruction, address computation is similar. We, instead of writing something to memory, we need to write something into register file. So we read from memory and put the result, put the data into register file. So address calculation part is taken care of. What we need is that output of data memory now needs to go back to the register file. So we need a multiplexer here. This multiplexer allows ALU output to be written into register file or data memory output to be written into register file. Okay, the register file address is coming from bit 12 to 15. Okay, next let's look at branch instruction. So in branch,
Excuse me, sir.
yeah.
Sir, why do we need to store the LU part like in the WD LU output?
ALU output is not going to WD. So see, the convention I've used here is that when you have wires crossing, if there is a dot, then they are connected. Otherwise, they are simply disconnected. So
Yeah, so
ALU
LU
output is
output we have a multiplexer, right? The previous one.
ALU output is going is being used as address for load store instructions. And for DP instruction, it is going through this multiplexer to WD of register file, the right port of register file.
Okay.
Okay. In branch instruction, again, we need some address computation. And we transfer that address to the PC. So here I'm going to use yet another adder for this, although it's possible to use ALU also for doing that. But in this, just to keep things cleaner, we take these 24 bits of the instruction and we need to shift it by 2 positions because it's a word offset and we want a byte address. So shift it by 2 position and do sign extension. The address is to be interpreted, this offset is to be interpreted as a signed offset. So now we already have this adder producing PC plus 4. And you recall that this offset is with respect to PC plus 8. So we need to add the offset, we need to do plus 4 more here. Okay. So there would be designs where this extra plus 4 is not required, but let's leave that out for the moment. So effectively, what we will get at this point is the current value of PC plus 8 plus the offset. Okay. And what is going to the PC as the next address is either simply PC plus 4 coming through this multiplexer or this target address for the branch. One of these to get selected. So this has to happen conditionally for a conditional branch. We need to, I've not shown here, so there would be flags which will be set by instructions like DP instructions, and that would decide whether branch is to take place or not to take place. Okay, but the skeleton of the circuit is here. We need appropriate control so that all the multiplexer I have introduced, I have omitted the select inputs. Okay, so all multiplexers require select input. ALU requires to be told which operation is to be done. You need to do write enable for register file and data memory. So all these come from a controller, which we are going to look at separately. But this gives a picture of the data path for the small set of instructions we have taken. Any question at this stage?
So could you explain what S2 was in?
Okay, so there is just okay, I have a slide for that. So 2 blocks I've labeled as EX or S2 are basically just manipulation of the wires. So EX block is to extend 12-bit offset coming from instruction to 32 bits, extension by 0 in this case. So extension, so on the right I'm showing how do you extend 4 bits with zeros to make it 8 bits. So you pass on 4 bits as it is and connect the remaining output bits to 0 constant. Okay. Sign extension means you replicate the sign bit. And there is also a shift of 2 which is required. So the lower 2 bits are connected to 0.
So like in this, the sign extension was because PC can be updated either positive or negative. Like, why are we doing the shift?
Shift is because the 24-bit offset which is given is a signed is a signed number, signed offset, and it's a word offset. Finally, what we want is a byte address.
So like if we pass 1, it will shift by 4 bytes.
Yeah. Yeah.
Okay. Good.
So this is the data path showing where you will have you'll need to feed control signal also. So I've just named the control signals. You PSRC is it's controlling the source for the PC. PW enables write into PC. RSRC, R source, decides which address goes to the second read port of the register file. RW is the write enable for register file. A source, it's the ALU source control. OP provides the decides the operation which ALU does. So here, so I'm assuming that ALU is also giving you the flag values which may be updated. So flag F set or flag set is a control signal which is active when flags have to be set. Okay, the value that has to be put in flags is coming from ALU. MW is memory write enable, and M2R is controlling this multiplexer, which is feeding data from memory to register file. Okay, so imagine that there is another piece of hardware which we call controller, which is producing all these orange colored signals. Okay, so that together with the data path forms a complete processor. Okay, so it's a simple design, simple to understand, simple to create, but this is not, as I mentioned, not the best possible design. There are issues with this. One problem is that each instruction requires one clock, but the clock has to be slow enough to take care of the slowest instruction. So what do we mean by instruction being slow or fast? So for each instruction, there is some path which is exercised. Okay, the data flows through some of the modules, and each module adds its own delay. Just 1 minute. So since the paths followed by different instructions are different, each instruction has different delay, and the clock period has to be sufficient to take care of the instruction that has the maximum delay. Secondly, resource utilization is poor. You can't share the resource. So suppose you want we have the addition capability here, but we are using additional adders here. Okay, can we do PC plus 4 by this ALU? That's not possible if everything is to be done in single cycle. In one cycle, ALU will do only one addition, and if you want to do more operation, then you need more hardware. Okay, so more resources. Resource utilization is poor in this design, and there are some instructions which are impossible to be implemented in this manner. Instruction which inherently require more than one things to be done in a sequence. Okay, we'll see examples of those, but you can imagine that if anything, for example, we talked about pre-increment and post-increment. So there is a sequencing. you have address calculation and memory access, or memory access and address calculation, and both these things would require state change and could be done. Uh, they would need to be done in a sequence, and in single cycle it can't be done. Some of these sequencing restrictions will come from the kind of hardware module which you assume. So, for example, register file, we assumed you have 2 read ports and 1 write port. So, if 3 things have to be read from register file, they can't be done in that can't be done in a single cycle. You need to read these in at least 2 cycles. So, these are the limitations of a single cycle design. Let's elaborate further on the timing part. Yeah.
Sir, in the previous slide where the data part that the whole diagram was made, you said the orange part comes from the controller.
Yeah.
So aren't they directly coming from the instruction set only? Like, what is the
Yeah.
op?
So in this case, controller is nothing but some combinational logic uh, with instruction as the input and these control signals as the output.
Okay, so the controller does some changes to the instruction.
No, it doesn't change the instruction. It looks at the instruction and figures out the value of these control signals in any given
Okay,
cycle.
sir. Yeah, okay.
So let's analyze the timings where we'll assume that not all components have 0 delay. So for registers, we assume that delay is 0, like we have only one register. I don't mean register file here, a single register. So PC has 0 delay. That means uh, at the clock edge, when you change the state of PC, it's the new value is immediately available at the output. The adders have delay, which I'm denoting by T plus. ALU has delay, which I'm denoting by TA. Multiplexer, we assume, have 0 delay. And register file has a delay TR. Program memory has delay TI. And data memory has delay TM. So the assumptions about register and multiplexer delay to be 0 is that compared to in real practice, compared to other delays, these are very small. So therefore, I'm sort of neglecting them. For register file and data memory, we'll assume that the delay is same in reading and writing. In general, reading delay and writing delay could be different. And bit manipulation component like EX and S2 have 0 delay, which is quite obvious. So now for every instruction, let us try to look at the path which is excited by that instruction and see the delay that will be encountered. So in fact, there'll be multiple paths. So we'll look at the worst case delay. First, we are looking at DP instruction like add, subtract, and so on. So starting from PC, first delay we encounter is the instruction fetch delay, or IM, which is TI. So here is the expression I'm putting. So TI is the delay we encounter in instruction memory. Then we are reading register values. So that delay is TR. Then we are doing some arithmetic operation in ALU. That delay is TA. And we are writing the result back into the register file. Again, a delay of TR is encountered. So this path which we look at the paths which begin in some sequential element, go through a few combinational elements and end up in a sequential element. So starting with PC, going through IM, going through register file for read purpose, going through these multiplexers, through ALU, this multiplexer, and back to register file. So that's where the path ends. And the delay encountered is TI plus TR plus TA plus TR. But the instruction requires another path. going from PC through this adder, through this multiplexer and back to PC. So T plus is the delay involved there. And the critical delay will be whichever is the larger of the two. Right? Let's look at delay of instruction. Yeah.
So don't we have another path? Like we have shown only two paths. One more should be this. It goes through the piece like this program memory, then adds the S2 and then +4. The third path.
Yeah, that path is not relevant for this instruction. So as long as data progressing through this path we have considered stabilizes, it's good enough for us.
Okay, sir.
So we are looking at the path which actually gets excited while executing these instructions. Okay, next we look at instruction of DP category, but which don't write the result in register file, like compare and test and so on. So in that case, the second TR component is not there, right? But rest is same, TI plus TR plus TA. Store instruction. Requires propagation through instruction memory, then register file, then ALU for address calculation, and TM for writing data. So TI plus TR plus TA plus TM, and of course T plus is there. Load instruction. Is there a question?
T plus is the delay for adder.
Yeah, T plus is the delay for adder.
The delay for an ALU be greater than that of an adder, like an ALU is more complex.
Well, not necessarily. You may design. You may use carry look ahead addition here, and you may be using just to save the cost. You may use carry propagate addition for this adder. So suppose you were using same addition technique in ALU and this adder, then of course TA will be same or more than T plus, and therefore the first term will never be dominant term. The second term will always dominate. But if you allow for the possibility that this path of PC plus 4 is a much more relaxed path, you can put a cheaper adder here, and this path is tight where ALU is coming in. You want to put fastest possible adder. Then we retain this term. I mean, this could become significant. Generally, it won't, but there's a theoretical possibility. Okay. Load is similar to store, but after memory access, you are also writing into register file, so the TR also gets added. And finally, branch. You have two paths. One is through instruction memory and through the second this +4 adder. Okay, so TI plus T plus, and there is another path going through both the adders. So T plus plus T plus. So 2 times T plus. How do we put these together? We take max of all these values. So overall clock period has to be greater than equal to max of all these terms. And some terms which are clearly contained in others can be thrown off. For example, T plus is irrelevant since we have 2 times T plus. Okay. And Ti plus Tr plus Ta is subsumed in others. So in fact, this one, Ti plus Tr plus Ta plus Tm plus Tr, one which came from LDR instruction, subsumes all these 3. So what typically that will be the dominant term, but one never knows about these 2. If you have used very slow adder and very fast adder here, then maybe this could be significant, but in most likelihood, this is the dominant term which will dictate the clock period. So all instructions will take time corresponding to what the load instruction takes. Right? So there is certain wastage of time here. Okay, that is all for today. Any questions?
Sir, in the load one, like we have the second TR, so that is used when we have write back, right? Otherwise, it won't be used.
Yeah, this is because the data you are reading from memory is stored in register file. Loading a register from memory. So there is a read register file is read, and later on you do write also.
Okay, sir.
Sir, you mentioned about the announcement for the quiz.
Yeah,
where?
quiz will be in the lecture hour of Saturday. Saturday, as I mentioned, it's a buffer day, so I also missed a class earlier, so I'm utilizing this. Within this time, within the lecture hour, towards the end, we'll have a quiz. And I know some of you have another quiz starting at 11, so I'll leave you some 15 minutes before. Okay.
So what will be the duration of the quiz and the mode of the quiz?
Mode of the quiz would be using grade scope. Okay, questions will be of short answer type. There'll be some 3 or 4 questions. I'm still working on that, and so you would get time slots for answering different questions. So the backup option. I mean, if there is any issue I see with grade scope, then Moodle will be used. But I'm right now trying for grade scope.
It will be objective type or written type, like we have to upload the
So
answer.
it'll not be a multi-choice type. There'll be short answers.
Okay, okay.
Yeah, which you will
So
have
we need to scan and upload.
The text will have to be keyed in. If there is a need for diagram, you could just take picture and load.
We'll have to type.
Like ARM based, no?
Yeah, text you will have to type.
Acha, okay.
They would be ARM based, right? Or
Yeah, this is for the. I have announced how many lecture. I think lecture up to lecture 7.
And the open book or closed book? Can we refer to the instructions?
Yeah, open book.
Okay.
So you can refer to book. You can refer to lecture slides. Okay. But don't consult each other.
So there would be like programming questions in ARM assembly or what?
That I don't know. I'm still working on it. You, of course, you won't be asked to write large program, maybe a short sequences of instructions. Okay, either interpret short sequences of instruction or write a few instruction for some operation of that kind.
So can we also use ARM sim during the assignment or the quiz?
Why would you do that? To
test if it's working or not.
Test. You could do that.
So will there be proctoring?
There'll be what?
Proctoring.
Proctoring.
Yeah.
No.
Okay.
No proctoring. Okay, close now.
Excuse me, sir.
Yeah.
Sir, when we, let's say, compare something, let's say we